Imagine having the ability to observe the deepest mysteries of the universe, from the first stars and galaxies to signs of life on distant planets. This is the goal of the Square Kilometre Array, or simply SKA, the largest and most powerful radio telescope ever built. The SKA is a project of gigantic proportions being developed by an international collaboration involving over 20 countries. It stands out for its ability to capture radio waves coming from extremely distant regions of the universe, as well as being capable of probing the sky with a sensitivity never before achieved. Unlike traditional telescopes, which capture visible light, the SKA uses radio waves, allowing us to observe phenomena that are invisible to the human eye. The Square Kilometre Array project began as an ambitious vision in the 1990s. Astronomers around the world recognized the need for a more sensitive telescope. This idea arose from the understanding that existing radio telescopes, though advanced, could not capture large-scale information necessary to answer fundamental questions about the origins of galaxies, black holes, and even the formation of the first stars. However, this idea could not be realized by a single country. The project's massive scope in terms of technology and resources required international collaboration on an unprecedented scale. Throughout the 2000s, more than 20 countries joined forces to turn this project into a reality, forming what is now known as the SKA organization. In 2012, after years of planning and debate, 2 remote locations were chosen to host the SKA's antennas: the vast semi-arid Karoo Desert region in South Africa and the remote plains of Western Australia. The selection of these sites was no coincidence. They were chosen due to the low interference from human-produced radio signals, allowing the SKA to observe the universe with minimal interference. The construction of the SKA was divided into phases, with Phase 1 involving the installation of hundreds of dish antennas in South Africa, known as SKA Mid, and thousands of small dipole antennas in Australia, called SKA Low. This immense network of antennas will operate as a single giant telescope, with a total collecting area of more than 1 square kilometer. The project has ambitious expansion plans, with Phase 2, known as SKA-2, promising to further extend the telescope's coverage by integrating antennas in other countries in Africa and Australia, transforming the SKA into the largest and most powerful telescope in the world. The secret behind the SKA is the use of a technique called interferometry, which connects all these antennas to work together. Although they are spread over thousands of kilometers, the signals captured by each antenna are combined by supercomputers, creating the equivalent of a telescope with a gigantic aperture. This technology provides extremely high resolution, capable of distinguishing very small details in very distant objects. The volume of data generated by the SKA is staggering. Each day, the SKA will produce more data than the entire global internet traffic. This requires a massive processing infrastructure, with some of the most powerful supercomputers in the world. These computers not only process the data in real time, but also store it for future analysis. To handle this challenge, engineers have developed a highly efficient data processing system, using cutting-edge technologies in artificial intelligence and big data. All this computational capacity is essential to transform the radio signals captured by the antennas into detailed images of the cosmos. It's important to note that the SKA is not just a scientific achievement, but also an engineering one. Building this giant network of telescopes in remote regions like the Australian desert and the South African savanna required innovative solutions. Each antenna was designed to operate in extreme environments, withstanding high temperatures, strong winds, and complete isolation from human-made radio interference sources, such as cell phones and satellites. Moreover, communication between all these antennas and the data processing centers requires a sophisticated and extremely fast fiber optic network. Over 65,000 kilometers of cables connect everything, ensuring that signals are sent to the computers almost instantly. The Square Kilometre Array is not just a technological advancement. It represents a giant leap in how we explore the universe. Among its main scientific objectives is the study of the origin and evolution of the cosmos. With the SKA, it will be possible to observe deeper into the universe's past, exploring the cosmic dark ages, a period shortly after the Big Bang when the first stars and galaxies were just beginning to form. The SKA will be able to detect extremely faint signals that have traveled for billions of years through space, revealing unprecedented information about the formation of cosmic structures. Another fascinating goal of the SKA is the search for extraterrestrial life. Its highly sensitive antennas will be capable of detecting possible signals from advanced civilizations on distant exoplanets, expanding our ability to investigate the possibility that we are not alone in the universe. Additionally, the SKA will play a key role in the study of dark matter and dark energy, the two biggest mysteries of modern cosmology. It will help map these invisible substances that make up most of the universe, shedding light on new data about their properties and behaviors. But the impact of the SKA goes beyond astronomy. The enormous volume of data it will generate, estimated at hundreds of petabytes per year, demands technological innovations in areas such as supercomputing and artificial intelligence. This effort will drive the development of new data processing technologies, with applications ranging from enhancing telecommunications networks to improvements in fields such as healthcare and cybersecurity. Furthermore, the SKA will contribute to the understanding of space weather by monitoring solar storms that can interfere with satellites, GPS systems, and power grids on Earth. By predicting these events more accurately, the SKA will help protect critical infrastructure and plan future space missions more safely. The current timeline anticipates that the telescope will begin collecting its first scientific data by the end of 2028. However, before that, there will be an initial phase of testing and calibration, with some limited operations starting around 2027. This initial phase will include approximately 10% of the SKA's total planned capacity, and full operations with the telescope at full capacity are expected to occur gradually as more antennas and systems are built and activated. The SKA's impact goes far beyond science and technology. It reinforces the importance of global cooperation and connects us to a future vision where knowledge and exploration go hand in hand.